All right, welcome everybody. Today we're going to talk about lesson number 69. We are still in section 9.2, so we're still going to be talking about arithmetic sequences, but now we're going to start adding those sequences up and turn it into something either called a partial sum or a series. Something important to note here in lesson 69 is not only are we going to review the formulas we've already seen, we're going to have new formulas for the sum of an arithmetic sequence, and then we're also going to see a couple calculus-specific formulas. So again, if you haven't been kind of creating a running list of formulas as we've been working through this chapter, I suggest you start doing so sooner rather than later. Before we get into the new formulas, I just wanted to kind of backtrack for 1 minute and talk about some of the formulas that I have already given you. So the properties of summations we saw back on virtual lesson number 2, and here we're talking about them as shortcuts. So when I told you about them originally, I had told you they were only true if you're starting at I equals 1. The truth is it's a little bit more complicated than that. Formula 1 is only true if you start at 1 because of the fact that the actual n is in the formula. So the reason why that matters is because if you were going from 1 to n compared to 5 to n or 20 to n, that n would be very different each time. So it's very important that you do realize that Formula 1 only works if you're starting at I equals 1, or else you kind of have to rewrite the problem or cheat a little bit. As far as formulas 2 to 4 go, these actually will work for any starting I because they're purely algebra based. If you take a look here at formula number 2, all you're doing in the formula is factoring out a constant. That is a purely algebraic maneuver. There is no n in the formula, so you're free to do that anytime. Same for 3 and 4. If you look at these formulas, they are purely algebraic. There are no n's in the actual formula, which means you're free to use them for any starting value of I. So whether or not I has to be 1 or not is very important. We're going to see some more formulas at the end of today's lesson where you do have to be 1 to start. But again, for these 4 formulas so far, the only one where you have to have 1 to start is for Formula 1. Going forward, just pay attention to when it has to be I versus when it doesn't have to be I. And again, I would strongly recommend that as you go through these lessons, you're kind of making a running formula sheet for all the formulas that you might want to use for a review day and also for an upcoming assessment. So another reminder, what does it mean to be an arithmetic sequence? It means that between consecutive terms, you have to have a common difference D. And remember, when you're looking for that common difference, you would always do the further term minus the previous term, the later term minus the earlier term, so back minus front. Another reminder that when it comes to arithmetic sequences, there are 2 different formulas. I'm going to use them interchangeably, as are you. I would strongly recommend you at least try to use both of them at some point, but certainly you're not required to use one versus the other. This is yet another new formula, so I suggest you write this down. You are only allowed to use this in a very particular case, when you are finding the sum of a finite arithmetic sequence. So finite means there has to be a clear start and a clear end, and arithmetic meaning it has to be something that is linear. So it only works in that specific case. Here is your formula. The sum of the first n terms would be equal to n over 2, where n is the number of terms, times a1 plus a sub n, where a1 is the first term in the series, an is the last term in the series, and then the s is what tells you that you're actually finding a sum. So it's a great formula, but again, it only works in the particular case of when you're finding the sum of a finite arithmetic sequence. Before I actually show you the formula in action, I want to make sure you understand why it works. Suppose you were asked to add 1 plus 2 plus 3 all the way up to plus 10. If you take a look at this, why is this arithmetic? This would be considered arithmetic because the common difference would be positive 1. If you take a look here, if you were trying to find some kind of shortcut for how you could add these numbers up as opposed to just doing 1 plus 2 plus 3, you would look at the first term 1 and the last term 10. Then you would look at 9 and 2. You would look at 8 and 3, 7 and 4, and 5 and 6. If you did that, you would realize that what you really had was 5 groups of 11. which means that when you add these up, you should in fact get a sum of 55. How can we take that idea of making groups of the same value and turn it into a formula? Well, that's exactly what we did. If you look on the previous slide, well, you're finding the sum. That means you need an S. How many things are you adding up? Well, between 1 and 10, there are exactly 10 terms. To find the sum of the first 10 terms, you're going to do the number of terms, which is 10, divided by 2. You're going to do the first term in the series, which is 1, plus the last term in the series, which is 10. If you go ahead and simplify that, that's exactly where 5 times 11 comes from, and you'll see that you'll get that sum of 55 either way. Obviously, using this formula is going to be much simpler the more things you're adding up, and also so you don't have to list all the terms out, but I want to make sure you understand why the formula works, and now we're going to go ahead and use it. So since these are simpler examples, I just wanted to show you ones that were already done. So in number 1, find the sum of the first 20 terms of the arithmetic sequence. They give you the first term, they give you the 20th term, and they're telling you exactly how many things to add up. Because we know for sure that it's an arithmetic situation, you're finding the sum of the first 20 terms. 20 divided by 2. The first term is 5, the last term is 62. Go ahead and do that multiplication. You get a total sum of 670. Please note that when you're finding sums, it is very likely that you're going to get large numbers. You can even get negative numbers, zeros, decimals, so don't be afraid for any of those types of answers. Let's say you're being asked to find the sum of the first 40 terms for this arithmetic sequence, 2, 5, 8, and 11. We know that it's arithmetic. We know that we're adding up 40 things. We clearly have the first term, but what we don't have is the 40th term. So the first thing we have to do is use one of our formulas from yesterday to calculate the 40th term. So between the 40th term and the first term, there are exactly 39 terms. Each of those terms is multiplied by the common difference, which if you do any term back minus front, you can see is 3. We then calculate the 40th term to be 119, and then we can go ahead and find the sum of those 40 terms. 40 divided by 2. The first term is 2. The 40th term is 119. Do those calculations for a sum of 2420. On assessments, the number one mistake people make on problems like this is they find the 40th term and then they forget that they're not done. They haven't actually found the sum. So make sure that if it is a two-step problem, you do both of them. For example 3, find the sum from 1 to 50 of 3k plus 2. So we are adding up 50 things. To find the first term, you're going to plug a 1 in for k. To find the 50th term, you're going to plug a 50 in for k. Once you know what the first and the 50th term are, plug it into your formula for a sum of 3925. If you notice those first 3 examples, all of them did start at a value of 1. So I want to talk about what happens if you're not starting at 1. So if you're not starting at 1, like example 4, you're finding the sum from 51 to 100 of 7n, there are 2 ways you can do this. One of them is kind of the more official way, which I'm going to show you first, and then I'm going to kind of show you a cheat way. Again, both of them work, but the thing about the cheat way is you have to almost do twice the thinking. So my advice is always just kind of use the formulas when possible, but I know some of you don't like to do that, so I'm going to kind of show you all your options. So first of all, just to in fact verify that this is in fact arithmetic, 7n would be equivalent to y equals 7x, so it is linear. Again, you have to verify that or else these formulas do not work. So because this problem does not start at 1, the best way to go about this would be to rewrite this problem so that it does start at 1. So you're going to find the sum from n equals 1 to 100 of 7n. Of course, you can't just change the problem. You only want the sum from 51 to 100. So if you rewrite it as the sum from 1 to 100, you're then going to have to subtract off the pieces that you don't want. So if you really wanted the sum from 51 to 100, but you rewrite it as the sum from 1 to 100, then you're going to subtract off all the things you don't want, which are all the values from 1 to 50. Again, that is really just an algebraic maneuver, so perfectly fine for you to do that. Now that you have 2 sums, you're going to have to use the formula twice, subtract, and that's going to give you your final answer. So from here, you're going to go ahead and do 100 divided by 2. Plug a 1 in, you get 7. Plug a 100 in, and you get 700. minus 50 divided by 2. Plug a 1 in, you get 7. Plug a 50 in, and you get 350. If you calculate the first sum, you get 50 times 707 minus 25 times 357. And if you do those calculations and subtract, you do in fact get the final sum, which is equal to 26,425. So again, a rather large sum, but perfectly fine that it's big. Again, this would personally be my advice for what you should do if you're trying to use one of these formulas that has to start at 1 in order to kind of just use it as is. On the next slide is another example 4, and I'm going to kind of show you the cheat. If you wanted to do the cheat of the the sum of the first n terms, you'd have to first calculate how many terms are you actually adding up. So in the previous slide, once you rewrite it as 1 to 100, as long as it's 1 to something, you're always adding up whatever the something is. 1 to 100 has 100 terms. 1 to 50 has 50 terms. Whenever you're doing it from something other than 1, you have to think back to that little cheat I showed you a couple of days ago. The top number minus the bottom number plus 1. So if you did 100 minus 51 plus 1, you are actually adding up 50 things. So if you want to kind of do this little workaround, this little cheat, the first thing you have to realize is how many things are you actually adding up. So if you realize top minus bottom plus 1, then you realize that you are adding up 50 things. So 50 divided by 2. If you're adding up 50 things, you're going to start by plugging in the bottom number, which is 51. That's going to give you 357. Then you're going to add in the top number, which is going to be 700. That is going to give you 25 times 1057. And as you should, you get the same exact answer as you did in the previous slide, 26,425. There are a lot of different formulas I'm going to show you and a lot of different types of problems. So honestly, as long as you can get to that answer, that's fine. But I would probably recommend using the previous slides method as opposed to this, but I do want to make sure that I show you both. Example 5, find the sum of the integers from 1 to 57. You want to realize that the integers is in fact an arithmetic sequence. It's an arithmetic sequence with a common difference of positive 1. Once you have in fact verified that, you are adding up the first 57 things. That means you're going to do 57 divided by 2. The first thing you're adding up is the 1. The last term, the 57th term, is 57. That's going to give you 28.5 times 58, which is going to make your sum 1653. Anytime you're asked to deal with the integers, just the regular integers, you're always going to be arithmetic and you're always going to have a common difference of positive 1. Whenever you talk about the odd or even integers, you have to make sure that you realize that the common difference is actually 2. That's true for if you're doing even or if you're doing odd. So you're doing the sum of the even integers from 2 to 100. Because you're doing the sum of only the even integers from 2 to 100, there are only 50 even integers. Okay, from 1 to 100, there would also be 50 odd integers. So just make sure that you are adding up only the things that I'm asking. So again, 50 things. So you're adding up the sum of 50 things, which is 50 divided by 2. The first even integer is 2. The last even integer is 100. That's going to give you 25 times 102, which is going to give you a sum of 2550. Again, pay no mind to whether these sums are small or large. How about the 12th partial sum of the following? So you'll notice here in example 7, I'm telling you to add up 12 things. You can pretty clearly look at it and tell that this is arithmetic and the common difference is -5. Make sure you make it negative. You can see the first term. What you can't see is the 12th term. So you have to first find the 12th term. Easiest way to find the 12th term is to realize that it's equal to the first term plus 11 common differences. which would mean that the 12th term was equal to 75 plus 11 times negative 5, which would mean that the 12th term is 20. That would mean that when you go to find your sum, the 12th partial sum, which means the sum of the first 12 things, would be 12 over 2. 75 is the first term. 20 is the 12th term. And if you do that calculation, you're going to get a sum of 570. Take a look at example 8. In example 8, I am telling you to find the sum. You'll notice here that, again, you can quickly verify that it's arithmetic, and you can quickly find the common difference is, in fact, 3. Interestingly enough, you know the first term and you know the last term. What you don't actually know is what term in the sequence is 61. And again, there's ways for you to kind of guess and check. I know that that works, but I'm just trying to urge you to use the formulas whenever possible. So if what you want to know is how many terms are there until you get to 61, what term number is 61? Well, the easiest way to do that is to use this alternate version, an equals a1 plus n minus 1 times d. You know that the last term is 61. You know that it's starting at 13, and you know that the common difference is 3. Subtract 13. Divide by 3. That then concludes that n must equal 17, which means that 61 is the 17th term in this sequence. So because you're finding the sum, that means you're adding up the first 17 terms. 17 divided by 2. The first term is 13. The last term is 31. And if you do that calculation, you get a total sum of 629. Little word problem action for you. So find the sum. So a job offer has a starting salary of $32,500 with an annual raise of $2,500. Find the total compensation through the first 6 years of employment. So first of all, you have to realize this is linear because you are getting an annual raise of the same amount. To think about what this would actually look like, you are being asked to find the sum for the first 6 years. So that would be from 1 to 6. The formula for this equation would be 2,500N plus 30,000. Why is it 30,000? Well, remember, the starting offer, unless I tell you otherwise, that's the first term. Whenever you're doing the formula AN equals DN plus C, which is what this is, the C is, of course, the 0th term. So you would have to subtract 2,500 from 32,500 in order to get the y-intercept, which is 30,000. If you then wanted to find the sum of the first 6 years of employment, you would have 6 over 2. During the first year of employment, you'd be making 32,500. During the 6th year of employment, you'd be making 45,000. And again, you would get those values by plugging in 1 and plugging in 6. And then, of course, if you're working for 6 years, you would hope to be making a fair amount of money, which is $232,500. Now, that is as far as the lesson goes in terms of what's going to be on the homework, but I also want to show you some calculus summation formulas. Please note at the bottom that these are not in your book and they're not on the homework, but they could very well be on the upcoming assessment, and you'll definitely need them for next year. So I would certainly add these to your formula list. Notice that you do need to start at 1 for all of these formulas because n is present in every single one. If you do not start at 1, then you have to add or subtract any of the extra pieces. So formula number 1, we've seen that before. If you're going from 1 to n of a constant, simply multiply the constant times n. That's not new. This formula here for number 2, this is actually a different version of the formula I showed you today that has all n's. I would, again, recommend not using this unless I tell you that it's a calculus problem, but this is yet another way for you to find the sum from 1 to n of just I or just n or just any single variable. Technically, this is arithmetic because 1, 2, 3, 4, that has a common difference. But again, I'd recommend not using this formula unless I say to. Here's a formula for I squared. So I squared is not arithmetic, but it does have a formula, n times n plus 1 times 2n plus 1 over 6. And then I cubed, again, not arithmetic, but it does have its very own formula as long as all the problems start at 1. So let's do a couple of these. If you are going to be finding the sum from 5 to 20 of I, the first thing you notice here is the fact that it's starting at 5 and not 20 is a little bit of an issue. In order to solve this, though, it's pretty simple. We're going to do a similar technique that we did earlier. Sorry, I put the formula at the bottom left-hand corner, but it might be a little bit, you might not be able to see it because of the toolbar there. So, oh, there we go. Perfect. All right. So from here, you're going to go ahead and rewrite this. Instead of having the sum, instead of the sum from 5 to 20, you're going to rewrite it so that it does, in fact, start at 1. You can't just change the problem, though. So if ultimately what you want is the sum from 5 to 20, and you rewrite it as the sum from 1 to 20, you're going to go ahead and subtract off the pieces that you don't want. And the pieces that you don't want would be the values from 1 to 4. So again, we are now going to use this new formula that is at the bottom here instead of the one today for arithmetic. Again, this is what you're going to be using when it's a calculus-based problem. So you're going to do n times n plus 1 divided by 2. So for the first calculation, n is 20. You're going to multiply that by 21. You're going to divide it by 2. In the second calculation, the n is 4 times n plus 1 divided by 2. If you perform each of those calculations, you get 210 minus 10 for a total sum of 200. So again, these last 3 slides, 10, 11, and 12, these are only when I say, use the calculus version of the formulas. So it's not in the homework, but it could be on the assessment. You'll definitely need it for next year. And I will continue to add these formulas to your list for easy access. Here, you're asked to find the sum from 1 to 10 of I squared minus 1, and you're actually going to use a couple of formulas here. You're going to break this up, first of all, that's using an algebraic formula. Then you're going to use both the constant formula, which is old, and the I squared formula, which is new. So I'm going to break this up into the sum from 1 to 10 of I squared minus the sum from 1 to 10 of just 1. Notice that I took this minus 1 and made it a subtraction and then a 1. You could also do plus negative 1, but it's easier to make it a subtraction. So if you're trying to find the sum from 1 to 10 of I squared, you're going to use that new formula from the bottom, which says you're going to do n, which is 10, times n plus 1, which is 11, times 2n plus 1, which is 21, divided by 6. Minus, if you're trying to find the sum from 1 to 10, and 1 is just a constant, then all you're going to do is multiply whatever the constant is, 1, times whatever n is, which is 10. The first calculation, 385 minus 10, gives you a total sum of 375. Last but not least, let's go ahead and find the sum from 3 to 10 of I cubed. So we need, first of all, the new formula for I cubed, which is there at the bottom. And then we also have to realize that starting at 3 is really no good. So we're going to rewrite this as the sum from 1 to 10 of I cubed. Subtract off the pieces that you don't want, which in this case would be from 1 to 2 of I cubed. If you use the formula twice, so n squared is going to be 10 squared times 11 squared, that's n plus 1, divided by 4. So 10 squared times 11 squared divided by 4, minus the n in this case is 2 squared. N plus 1 squared is 3 squared. Sorry, I think my stylus is a little dirty. Divided by 4. If you perform each of those calculations, you're going to get 3,025 minus 9, which is going to give you a final sum of 3016.